So let's look at the tickets. How do the tickets get on chain? So we have our tickets extrinsic, bold capital E sub T. What constitutes a valid tickets extrinsic? Well, it's this expression here. But let's start with this bottom bit because this is a bit easier. The number of tickets that were allowed in a block must be at most k. And we're only allowed to submit tickets if the lottery is still ongoing, right? If our epoch phase is less than y when the contest ends. This expression here ensures that gamma A cannot change after the epoch, after the lottery is finished, as closed within the epoch. Yeah. So there's a period of the epoch where you're allowed to submit tickets, and then a period after which you're not allowed to submit tickets anymore. At that point, gamma A is fixed, never changes. So that's 72. Basically, no tickets if we've closed. So what must this ticket say? Well, firstly, it's a sequence. So that's what this thing, it's a sequence of what? Well, it's a sequence of tuples. Tuples with two items. One is the ticket entry index, R. That's a number, 0 or 1. Remember, we get 2 entries per validator. And here is the clever bit. P. P is a proof. It's a ring VRF proof. And the ring VRF is this clever ZK snark enabled version of a Bandersnatch signature and VRF. Yeah, this is a clever little bit of crypto. We're not attempting to sign a message, which is why this message thing is empty. And our VRF is premised on this being a proof that the signer is a member of a set. The set in question is gamma Z. Gamma Z is the ring root. A ring root is essentially a commitment to a set of keys. In our case, the keys are the validator keys. So gamma Z is a commitment to that set of validator keys. And this must be a valid proof, which means one of those validators, we don't know which one, but one of them created this proof, and they did so correctly. They fed in this VRF input. And the VRF input, if you notice, it's the same form as the seal key. If we jump all the way back up here, it's the same form as this. Because actually, this signature is exactly the same thing that's happening in the proof of this, that this snark proves. It's actually the same bit of computation. It's just that this is done in a snark, whereas that's done in the open. Yeah? So when you come to sealing the block, you basically redo the ticket signing, but instead of proving that you can do it, you actually do it. And by doing so, you give away who you are. But it's the same XT. So I think the paper is too complicated for the iPad. It's the same XT. As up here. Now the entropy is different because now it's before, yeah? When we're verifying the ticket, it's the epoch before the ticket's actually, the seal's coming in. So here it's eta prime 2, there it's eta prime 3. And then we also add on this entry index R, which is the same term here. So these are actually calculating the same thing. This is just the snark proof that anonymizes which validator it is that's whose key is generating the ticket. Yep, that's the main difference. And yeah, XT is jam ticket seal, the same XT as the previous one. Now we have this N, right. So we define a convenience term, N, lowercase bold n. This is all of the tickets in our extrinsic. I do this quite a bit. I basically provide convenience terms that are causal derivations, like just pure derivations from extrinsics, because usually the extrinsic has stuff that we want to make sure is correct, and then we want to extract the information once we know that it's correct. So there's usually a bit like up here where we check that the extrinsic is correct, and then there's a bit like here where we extract the useful information from the extrinsic and ignore all the stuff that's just to do with checking it's correct. So what are we extracting? Well, we're extracting the entry index, and then we're extracting the calligraphic Y P. P is the proof, and calligraphic Y pulls out the VRF output of the proof. What is the VRF output of the proof? Well, if you remember all the way back here, we use calligraphic Y of the output here as well. It's this nice little high entropy, not so biasable VRF output that we use as the ticket ID. So this is in fact the ticket ID, and we use that as the identity. So we check that the seal is the same. When we check the seal to check its VRF output, we make sure it's the same as this, and that guarantees that it's the same key to a 1 in 2 to the 32, 2 to the 256 chance. And it provides us with an ordering. And therefore, we can score them, and we can just keep the lowest 600. Right? So we have these two things, Y and R, and they end up being our ticket. If we look at C, definition of C, it's the same Y and R. Yep. Okay. And so this gives us all the new tickets. Lowercase bold n are all the new tickets, and then we know that they're correct. We've defined them as being correct as 71 and 72. And we now know their ID and their entry index. What do we do? Well, we've got some funny notation. We take the n, and we ensure that it's equal to n deduplicated and ordered. No, I think just deduplicated. It might be ordered as well. Yes, it is ordered. So firstly, we ensure n is the same as itself having deduplicated and ordered all of its elements, all of its Y subscripted elements, so all of its scores. So we ensure that they're already in order and there already are no duplicates. That's what this term 75 means. We also ensure that all of the ticket IDs are distinct from all of the ticket IDs which we already know about, which are already in our accumulator. That's what this term 76 means. The funny thing here, this means disjoint, set disjointness. And we make sure these two sets are disjoint, i.e. all the tickets that are coming in are new. They're not already in the accumulator. Finally, we ensure that when we add in all the tickets into the accumulator, we get a final accumulator value that contains all of the new tickets. What this means is that all of the new tickets that we're introducing through the tickets extrinsic must actually be useful. Yeah? We don't want to be wasting our time processing tickets who don't score well enough to make it into the accumulator. So all the tickets that are being introduced on-chain must have a good enough score that they actually make it into the accumulator and displace, potentially, some pre-existing ticket that was in the accumulator. So this equation 77 just defines the new accumulator. Basically, it's just the old accumulator, but with the new tickets. And then we just take the best E, the best 600 of them. So X is a member of N, our new tickets, together with, nothing if it's a new epoch, and gamma A, our previous value of the accumulator, if it's not a new epoch, right? So we add the new tickets onto our previous accumulator unless it's a new epoch, in which case we don't. And then we order them by the ticket score, ticket ID, same thing. And we pick the lowest, the first 600. And that is the new accumulator. And then 78, just as I said, guarantees that we're not introducing redundant tickets. We're not introducing any tickets that don't make the cut. Good. I think we've been going a while. Let's take a short break, and then we'll jump into recent history. So, 2 minutes. Welcome back. Hope you ate well. You should now know everything there is to know about Safrol. No, not quite. But you should have a pretty good idea about how to interpret it in the grey paper. We're going to move on now. I was planning on doing questions, but honestly, I would prefer just to get through as much as possible, and then maybe we can have some questions at the end. Yeah, I mean, I'll try and make time for questions at the end. The next section should be pretty easy. Recent history. And for what it's worth, if you look on the left-hand side, you'll see you might be able to just see this bluey, greeny line here. That's where we want to get to. Okay. So we're going to try. We got 7 pages, so let's try.